Okay, so David's going to talk to us about Python and binary C, please.
Yeah. So yeah, Rob talked about API functionality already in the previous talk, and I'm going to talk about the specific Python interface that we have. So this was developed in the recent couple of months. Okay, so I'm going to introduce this, show some use cases and examples, and talk about future development things. Okay, so what is this? It's a Python wrapper for Binaryc using the Binaryc API that Rob has written, and a Python wrapper around this. And it's developed because well, people thought it would be useful and easy to integrate into other things, and it indeed is. A lot of people are now using Python. It's like the first year course in a lot of universities, first year programming course, so it's easy to learn, and thus having a Python wrapper for Binaryc would be a nice thing. I must say that the things I'm showing is work in progress. It didn't have a real release yet, but I will do that soon. Okay, so how can we see this code? We can see this on Surrey GitLab in the following link. And I just realized we have not put this on a public repo. Rob, maybe you can make it public. No, so but yeah, at least people can look at the code now. I will try to make this available on PyPy, so we can pip install this package. It still requires a working Binaryc and the shared library, and you also need the Python 3 for this. Python 2 is deprecated within 2 months officially, so well, yeah, end of life.
All right, I've made it public.
Okay, nice.
Hopefully, if someone could try going to that link and see if you can get to it.
Yeah, so people which are tuning in, try out the link. If you can copy it. Okay, so in order to make this work, we need to add a couple of things to the Python path and the library path. That will also be solved if we install this with pip, because then everything is automatically in the correct paths. To install this, it's just a make, but again, in the future it will be pip install, and more instructions are in the README. Now this code has 2 main parts. The real Python wrapper, it's called Binaryc Python API with underscores, and this is built with the Python C API. This is one of the solutions to wrap C code. Other things are Cython or CFFI, but this solution was we found parts of this. Okay, thanks, Mathieu. Very good. We found parts of this on. Where did you find this actually, Rob? On GitHub, right?
So the original Python version was by Jeff Andrews.
Did he inform you about this?
No, I found it by searching for Binaryc on Google.
Okay. Well,
so
Googling.
Google found it for me. And so I wrote to Jeff and said, can we use this to do stuff? Because he hasn't touched it in a few years, a couple of years. And I was already looking into how to wrap Python or wrap Binaryc in Python. And then I was looking at C types, I think it was, which is very complicated.
Yes.
Whereas the way he did it was much simpler. And I'm not an expert in Python, so I'm quite happy to copy paste this stuff. So I had updated it for the latest Binaryc, and then I gave it to you.
Yeah. So yeah, we found a nice solution, and we built on from this. And then there's the Binaryc Python without underscores .utils, and this is a set of extra functionality which imports this wrapper. And well, I've written some handy functions that manages like parsing output and stuff. These things will be combined, because this is a bit of a confusing setup now, but these things will be combined in one code. But I had some struggles with the setup.py. The thing is, in order to make the Binaryc API, you need to compile a lot of things by using libraries of Binaryc and Binaryc config in order to really have setup.py execute this is a bit unclear sometimes. It's a bit of a weird setup anyway, but I've almost got it working, but not in this version. Okay, so the Binaryc Python API has a couple of core functionalities, and one of them is run binary, which does exactly what it says. It runs a binary system with the argument string that Rob already talked about. And so you put it in here, for example, mass1 is 10, and then it uses all the default values that Binaryc has in order to set up the system, run the system, and then this outputs all the output that running this with the normal Binaryc would give. So the thing is, the log every time step has the instructions to log everything that gets logged, and then it is given back to Python. And then we have a couple of variations on this. One has, okay, so we can also build a log file, which is like a summary of the evolution of a binary, where you see stellar type changes, source slope overflows, common envelopes. These things are all like events in the lifetime of this binary. And on default, this is not active, but you can run it in a different way by using the with log file and then also passing the arguments. And then there's a functionality that's called run binary with custom logging. And this is very convenient because what this does, we can compile a custom logging library on the fly and give this to Binaryc, also using the API, and then it uses also that function to log some extra things. And now the nice thing is we can stay within Python, decide what we want to have outputted, logged, and then it will, behind the scenes, this will get handled. This was an interesting thing to make because I have to use Python to build the code that gets compiled, compile it with all the flags and libraries necessary, and then load it into memory using Python, and then pass the memory address to Binaryc, and then everything gets done, and then we get it back. Again, this is very convenient because we can stay within the Python environment. We don't have to go to Binaryc, recompile everything to get a custom output. Oh yeah, and there's some extra functionality, namely the return arg lines, which returns all the arguments that Binaryc version has. So we know, okay, with this version, these are the options that we can give Binaryc, and possibly in the future there are some extra functionality. Let's see the next one here. Okay, so what I will show now is a notebook with some working examples in this. Let's see, find it. It's here. Okay, so yeah, everybody sees this as well. So I've made a notebook in showing how to use this. For now, it's a 2-line import. If everything's correctly placed in your Python path, everything will be usable with pip soon-ish. But this works for now. So you can execute it, everything gets loaded. And as an example, here is the run binary. So you see here, this is the module, and then the function is run binary, and the arg string is the thing that we have set up here. So we give values for the separation, well, we set it to 0, orbital period, eccentricity, metallicity, etc. We build this argument string, and then we execute this, and I show the first 10 lines. I have a set of extra output for other examples, but the first 10 lines look like this. Okay, so this is a very simple example, but from here we can just use Python to output everything what we want. Now we can also output a log file. Here I write this to a temporary dir, and I execute it again, and this is then. So the speed is great. I mean, there's very little overhead apparently. I have not very well tested how much overhead there really is, but it seems to work very fast. And here we just see, okay, this is the one system, and these are the things that are happening. Quite a set of things. Now I'm thinking in building some utility functions also to automatically parse this log file to see if, filter on a common envelope, for example, and whatnot. I mean, you can think of any interesting thing that you want to build in Python and just use these log files.
I think you might be better off defining your own output.
Yes, also, yeah.
Because the format of this is not guaranteed to be the same.
No, that's true. Okay, maybe I'll change something in this if it's indeed not the same.
Well, it doesn't change much, but occasionally you get something at the end which I'll add. If there's new functionality put in, then I'll put it here. So, for example, here you can see the bit about the random buffer, random number generation stuff, which is just useful to show it's working.
Yeah, but this last column is the changing column, and the rest of the columns
the rest of it should be the same.
Okay, so but if we parse the last column in a more flexible way, then that would be nice. Okay, so this is all very basic still. Now here's the thing that I've been working on in this project for a bit. This is also in Perl, and I sort of got inspired by Rob's solution to this. So what if we do not want any of the standard outputs that Binaryc does, but we want to have a customized output? And the two working examples here are outputting only two things. Doesn't really matter. It's a proof of concept. So you can, with the custom logging functions and autogen logging C code, you can generate the necessary C code for building this logging, and you can decide, okay, the first, this is called the header part, is to catch this output. We call my stellar data or whatever custom logging line you want, and then we input have this logs model.time and *0.mass. Now you can also give the exact logging statement, like a printf, or if you want to make it a little bit more complicated, you can say, okay, if model.time is greater than a certain value, then log something, or if both stars are black holes, then you do it. So if you want to have anything like a little bit out of the ordinary like this, then you just build this part yourself. And now this gets, the code will get built around this, and then we, with create and load logging function, we really compile this extra library and load it into memory. And then the memory address is this func mem address. Now, if you do something that's wrong, it will complain already here. So it tries to compile it, but this extra shared library cannot compile if there's any error in it. So Binaryc C will not run anyway. It will just complain already. Okay, and then we, same example as here, we have some input that we want to evolve the system with, and then if I run this, then okay. So all the other lines that you see, those are included as well. So it's not an if-else, but it's both of the things gets outputted. But here you see is my stellar data. That's the thing that I used. Time is 0, mass is 15. It gets outputted like this. The nice thing is if you print it like this with time is 0 and mass is 15 or mass is whatever, then you can also build like a parser to automatically find the variables or parameters that you're outputting and put it in a nice data structure. So here's some more of the useful utility things that I've made. Run system behind the scenes does run binary or run binary with custom logging or whatever, and it checks this based on the things you give as KW args. So instead of building the argument string, you can just give it as an argument to the function, and behind the scenes, this argument string gets built. And now what I can do is I execute this, and with the function parse output, I catch all the output that this binary C evolution gives, and I select the thing that starts with example header 1, for example, or example header 2. And what I can then do is I put it in a data frame with pandas. It's a very nice tool. And then you see, okay, everything that starts with example header 1 gets caught, parsed in the correct way so that it's built in a dictionary and then put in the pandas data frame. And pandas is a very useful utility. You can query on this, you can select whatever. So from here on, it's whatever you want to do with the data, but this is a very useful way to parse the output. Now this is all designed for single systems, or well, binary systems, but one evolution. If you want to do this with a population, the code is not ready for that yet. So this is all if you have one single system and you want to inspect how the evolution goes. Now what I said is this example header 1 has these extra output, namely mass2 is 20, for example. If it's structured in that way, then it automatically finds that variable is called like that. If you, however, do not write it like this, but you just output the values of this, then it doesn't really know what columns are which. But you can, with pandas, for example, you can set, okay, the columns I know are time, mass, etc. So you can still afterwards query on this. Okay. And now the same example with a custom logging. So again, I output model.time and mass, and I put this in a nice data frame, and from there on you can plot things. You can select on the systems that you want. Okay, another example that I used recently was in order to see how much mass stars of a given mass lose on the main sequence. So from the beginning of when jumps to the end of the main sequence. So I wrote a small function for this to parse certain output, but you can build this in any way you want. Make a data frame out of this, and then select in this data frame the times when the first and the last of the main sequence, the time that corresponds to this, slice this, and then calculate the initial and final mass, and then decide what fraction it has lost within this time. And then I made a loop to sort of run a population to mimic this. Don't do this with a lot of systems because there's a lot of overhead. In the future, we will be able to do that in a better way. And so this took 14 seconds for 75 systems, so that's not too slow. And then what I did is I plotted the output of this. So all within a Python framework, you can now just inspect very easily, okay? We have a couple of systems that we're interested in. How do they behave at certain values? You see for different metallicities, they lose a different amount of mass, but all from, only from 7 solar mass onwards do they lose a significant amount of mass. Okay, so these are the examples. These are included in the Git repository, as well as a PDF of this. So if you do not have a setup, you can look at the PDF. It's the same thing, but in PDF format. Okay, so now back to this. How do I get this back? Okay, so that were the examples. Okay, so I've also made some documentation, not really by hand. There's a very nice utility called Sphinx, and if you correctly comment and format your code, then it will automatically read out this document from these comments and then make a PDF out of this. Some parts are in C code, and I want to use Doxygen for this. I have yet to find a very good working setup to combine Doxygen and Sphinx, but there are solutions to this. One is called Hawkmoth, but it's a bit difficult to get it working. What I then want to do is I want to put this on Read the Docs to have a nice website being hosted on this with working examples. This is all via the nice standards of building a package with Python. Okay, this is still subject to changes. I'm going to change the structure of certain parts of the code, and I am also still learning how to use Sphinx. It's a very nice package, but there's a lot to learn about this. Okay, and a couple of use cases that I thought of would be, well, at least I think are useful. So I sometimes had, when I was analyzing a population of stars that I got, some of these stars or some of these entries, they were puzzling, and I wanted to know a little bit more about their evolution. Now the nice thing is, if you use pandas or notebooks to analyze your data, you can now also import the Binaryc Python package and just run that specific system from within the same notebook and just analyze, inspect. This is the data exploration that you can do. It also is easy to combine with other packages like AstroPy, GraphPy for gravitational waves. There's also YT, that's a bigger simulation framework. I have not used this yet, but people can play with it and give me suggestions. I was thinking of some nice visualization tools, and I know that Miron van der Kolk last year made a binary evolution like with matplotlib, some of the things that you sort of make a little video out of the thing that you simulated. And also making Van den Heuvel diagrams on the fly would also be a nice thing to do. Writing a script in Python is trivial for this, as long as you have a couple of images, but I've seen the images on the website of Binaryc for this, so it's also easy to do. And another thing that I think is interesting, this could be used for educational purposes. So instead of having every student build their own version of Binaryc, successfully or unsuccessfully, that should not be necessary now, because you just install on a server, you design a server, you set up one Binaryc, and everybody just uses the API to that one installation, using the custom logging functionality, and then you have a whole classroom playing around with Python, but not having to touch any of the C code. So it doesn't require anyone to also learn C and go into the Binaryc documentation or those things. You can just have a very low threshold situation where a group of students plays with the data. Okay. Okay, so the future, I need to restructure some code and improve the documentation, but I guess that's always work in progress. I will combine these two parts into one package and make it available on PyPy, so we can pip install this. Again, you still need a working Binaryc, but yeah. Some things for functionality that I thought might be useful, if we can design something in Binaryc to give information to Python about which units the outputs are, we can use AstroPy to automatically also read out this. So, and with AstroPy it's useful because you can convert everything easily and have all the units correct. So the thing we talked about today as well was Binaryc help, and then one of the arguments that you could give. I will also build some functionality for this Python package to interface with this. And then this is a bigger thing that we have yet to decide to really do, is a functionality to run populations. We talked about this before, but it's a bit of a daunting task because the Perl packages are very big, and it's a very well written code. So, replacing something that's working might not be the best idea. So what this package does, it gives something extra, new functionality, or easier, more flexible. But running populations is something that we have yet to look into. There's probably people that want this, and so we can discuss if there's a big need for this. Or oh yeah, and I thought maybe we can design a cool logo, because I can think of a combination with the Python and the binary system. You know, if someone wants to help me out with thinking of a cool logo, that would be fun. Yeah, so this is my first time writing a proper module. I want to do it correctly, but you know, keep in mind it's the first time. Feedback is more than welcome, and feature requests are certainly more than welcome. And that was what I wanted to tell.
Okay, thank you.
Yeah.
I get 4 thoughts. I get.
Sorry.
So before we go on, so if you want to talk about
color background.
yeah.
Absolutely. So in terms of units, something I didn't mention today, there's a file called Binaryc physical constants. Whenever you want to use units in Binaryc, they are defined in there. And there are 5 fundamental constants, I think. 5, 6. Speed of light, gravitational constant, Planck, Boltzmann, electric charge or electron charge, and the Avogadro constant. Everything else follows from there, except for some others, such as the solar radius, astronomical unit, things like which you have to define because they're measurements. But essentially, everything follows from those. And actually, we had an issue in Binaryc a while back. Things didn't really agree, and I was trying to work out why. And it's because someone had used their own combination of constants and then chopped off a load of decimal places, which messed things up. So instead, I derived everything from this. So we have derived a whole list of derived constants, which are just based on these fundamentals.
Sure.
So you may want to see whether those agree with AstroPy or
Yeah.
these other. And the reason, and AstroPy probably does disagree with these because it depends where you get your data from.
Yes.
For G
Yeah.
or C. Or
Sure.
Well,
Yeah, so for example, the constants used in Mesa and the ones in AstroPy aren't the same.
there you go.
Okay.
So
So it's the same problem.
I ran into that issue
Um,
a while back.
So as long as you know that's happening, you can. I mean, you can always redefine these to whatever you need.
But that might be a good disclaimer. If we do build functionality to have units properly, then disclaimer could be like, okay, these are local used units.
We could even put something in that at compile time sets these to be whatever AstroPy is. That's also possible. That's actually very easy to do with Maison, so we could do that. You just have to undefine these and then redefine them. That's true. That could be done. And then you also have to bear in mind that AstroPy is also not constant.
No, that's also an evolving thing. Yeah.
So you know, they may change their measurement for G or something depending on you.
Sure. Don't think it's going to be changing very much. But
You'd be surprised. It makes a hell of a difference. You have 2 options in Binaryc: 6.67259 times 10 to the minus 8, 6.67408 times 10 to the minus 8. It gives you links to where you can find them. That's the 2004 recommended value. So that's the best I could find at the time.
yeah, but this is about the constants that are used. But I was more hinting about the units that things are expressed in. And it would be cool, but I don't know how much effort this is to build this in Binaryc, to read it out at least.
It's very easy to output everything in whatever in CGS or whatever you want.
Okay.
That's
Well,
very easy.
if we can do CGS in units.
Well,
then,
so everything is, so you have these macros, rsun, lsun, msun, so you can multiply them and then get everything in CGS. But it's in CGS because that's what's common in Astro.
Yeah.
There's also, the only one that's difficult, I think, is the angular momentum, which is stored in some dubious units in the code, in terms of rsuns and stuff instead of centimeters. However, there is a macro to convert. Yeah. So just call that, and that will convert easily for you. So you don't even have to remember what the combination is. But you can go both ways. But that's the only one that's difficult. I mean, times, mega years, everything else is.
Sure. Yeah, but it has
And
to be machine readable in a way that I can automatically read it.
I think that's also out. You can put that in the module. It should be easy.
Cool. Yeah. Sure. Okay. Yeah.